This lesson is on equilibrium, and we've already seen some equilibrium in the lab with some color changes and stuff in Le Chatelier's principle. And here we're going to talk about things like equilibrium concentrations and equilibrium constants and put that together with what we learned in lab. I'm going to start off by just reminding us of our physical equilibrium. I think people have an easier time thinking about this kind of equilibrium than a chemical. A few things about equilibrium. You have to have a reversible reaction. The arrow is going both ways. If the reactant or product is very much more favored, then you'll just have the reaction go in one direction. The other thing is the rates are equal, and we've said that quite a bit. We have to have evaporation occurring at the same rate as condensation. And the other thing is we say it's dynamic, and that means that nothing stops when we reach equilibrium. The reactions are still going. Okay, and then on this case we would warm it, and remember that affects our equilibrium position. And so we would say the word is equilibrium position is shifted to the right, because now we have more of what is our product, a higher concentration of our product. So just I wanted to remind you of this, this idea of equilibrium position is basically saying at equilibrium, which form do we see more of, the reactant or the product? Let's look at a chemical equilibrium. And I have a reaction, and one thing that's really helpful with chemical equilibrium is to think about it happening slowly. Some chemical equilibriums do, but many happen so fast that it's like you mix things together and boom, it's at equilibrium. It helps to think about it being a process where it takes a little while to get there. And it does sometimes. So what I've got here on this graph is that I'm graphing the concentration of the different substances over time. So I'm going to start by mixing them, and when I first mix them, there won't be any C. I'm going to just mix A and B, and then we're going to watch to see what their concentrations do over time. In other words, I'm going to expect the concentration to initially build up because it started at 0, and as the reaction goes, it'll build up. So let's see what happens. Okay, so it changes for a while, but then it reaches a place where the concentrations no longer change. And this is where we've reached equilibrium. So those concentrations are equilibrium concentrations because it remains constant at that point. Remember that at equilibrium, the concentrations do not have to be equal. In other words, we don't have to have the same amount of C as we do B or whatever. It's just what's favored. I would say that this reaction favors the reactants. Its equilibrium position is to the left a little bit because the reactants concentrations are higher. And by the way, when we have these reactions that go both directions, you know, sometimes it's confusing of what reaction we're talking about, the forward versus the reverse, because in the reverse reaction, C is the reactant. So by default, when we just refer to reactants, products, reaction, we're talking about the forward. Okay. When we say reverse, then we're thinking about C being a reactant and these being products. So anyway, we do have kind of two, and sometimes we don't say the forward reaction, but that's kind of the default. Anyway, so it is a property of a reaction where the equilibrium position will end up being. And each reaction has a kind of a set point that it naturally will go to. And we'll talk about how to calculate that and also the things that might change that. So if I have just a generic reaction here, I can make a constant. So this constant is a number that represents this reaction and where its equilibrium position is. These products over reactants. Notice that what I've done is I've taken the coefficient and turned it into a exponent. These brackets, the brackets mean molarity. So I'm talking about their concentrations. The concentration of C raised to the power of its coefficient times the D raised to its coefficient. So it is products over reactants set up like that. This C means it stands for concentration. Sometimes we do talk about, like I generally kind of do a KEQ because EQ meaning equilibrium constant. I say equilibrium constant a lot, but there are others, and we're not going to show them, but there are other ways. We will see Ka later. All of these are forms of equilibrium constants. But anyway, so that's Kc is the one with concentrations. Okay, when this is set up right, the concentrations that you put in here have to be the equilibrium concentrations. It can't be the concentrations when you first mix it. These are the kind of where it ends up, gives you this ratio. And then notice that it's unitless. No matter what your exponents are here, and I know they have molarity as a unit, they are defined as unitless because later in chemistry you start using activities instead of molarities, and those are unitless, and it makes the math work. I guess that's the easy way to say it. So in summary, the equilibrium constant basically tells you the position by putting the products over the reactants. And so if this number is large, it tells you we have more product form, and if it's small, then we have more of the reactant form. So what we just said before, if the Kc is large, and we remember that the equilibrium constant is products over reactants, then it being large means that the products are favored. And if it's small, it means the reactants are favored, just according to this equation. If it's near 1, that means that the equilibrium will have a mixture of both. Okay, sometimes you have an equilibrium where all the reactants and products are in the same phase, and sometimes the ones that are in different phases don't count for the equilibrium, and it's because in the equilibrium their concentration is not changing. The equilibrium constant is really based on kinetics and rate laws of chemical reactions. And for those, anything that remains kind of constant during the reaction is not considered part of the rate law. But anyway, so let me show you how this works. So if you have more than one phase, in other words, here I have some in the gas phase, and then I have this one in the solid phase. Well, when this reaction, if you could imagine, you have a solid, and there's some gas that's reacting and bouncing around on it. The concentration of the solid's not going to change, it's just there, but the concentration of the gas will change. And so the concentration of the solid kind of gets rolled into the equilibrium constant. So you might think it's something like this, and you see how we set it up. We took the C as a product, raised it to the second power because of that 2. And then these are both to the first power because the coefficients are 1. Well, that's not right, though. What we need to do is just leave out that solid. So this is the correct equilibrium constant for that equation. So the rule is what you leave out, solids, liquids, or solvents, their concentrations. And it's because, like I said, their concentrations don't really change during the reaction. They're pretty steady compared to the gases and the solutes in solution. And so they are already built into our constant K. Let's look at calculating an equilibrium constant. So if we have a reaction, say we put together A and B, and we let it sit for a while and reach equilibrium. And after it reaches equilibrium, we determined the concentration of each one. So these are equilibrium concentrations after it's mixed and it's reached like its happy place, right? So then the equilibrium concentration expression, that's where we use the equation and the coefficients. So what I would do, and so, expression is the word for this. It's the equation that defines KEQ or KC. And so what we have, the way that we got that, it's always products over reactants. There's a 1 there, so that's to the first power. There's a 1 for A, first power. The 2 ends up here, so as an exponent. So if we wanted to calculate the equilibrium constant, this Kc, we would plug in these equilibrium concentrations, like so. And then we get a number, and it's less than 1. So we would say that this reaction favors the reactants. Okay, let's look at one more slide and then we'll switch videos. The dissociation of water, sometimes called the ionization of water, is an important, very important equilibrium reaction. This reaction heavily favors the liquid water. Very little of water is in this ion form at equilibrium. So when we get its equilibrium constant expression, we would put products over reactants, but the reactant is a liquid, so remember we leave that out. So we're just going to have this for our Kc. And for water, the Kc is this number. It's a very, very small number. What does that tell you about the number of ions in water? Well, since hydrogen ion concentration times hydroxide ion concentration equals this very, very tiny number, it tells you not very many of the water molecules are in ions in water. We'll be looking at this equilibrium. It plays a huge role when you start talking about acid and bases in water.